Okay, I think you start. Dear colleagues, friends, welcome to this HBPS virtual lab visit. Previously, we already have okay, I think I have some echo here. I think I know how. Sorry for this. Okay, let's make it again. Good afternoon, everyone. Good morning, good evening. This is Lee from Technical University of Denmark. Today we are going to have the third HBPS Young Professional Virtual Lab visit. This time we have this Budapest University of Technology and Economics. Previously, we already have two successful events from two famous university, and today we are going to learn a lot from this high voltage laboratory from this Budapest University of Technology and Economics. Today we have three presenters, and they will present their excellent work from their research. I think now I can over to you, to our colleagues to present. Yeah. You can start now.
Ladies and gentlemen, very warm welcome to the Budapest University of Technology and Economics. My name is Richard Csalko, and I have two colleagues, two esteemed colleagues with me, Dr. Bálint Németh, who is head of our research group, and Dr. Levente Rácz, who is assistant lecturer at our group and laboratory. My colleagues will give you an overview of our university, the activities of our research group, and some details about the work that is being done in the laboratory. And I will then walk you around in the laboratory and show some actual experiments and see how we do this. So I would like to give the word to Bálint. However, he's having some connection issues right now, as far as I see. So I'm asking for a second of patience. Yeah, he's there now. Please add him to the stage. Mhm. Okay. Jen, Bálint is right now in the backstage. Can you please add him to the show?
Albin, can you make that? Because now I'm not the host. Yeah, I think now we can see something.
Yes.
Can you hear me?
Yeah, it's working now.
Can you hear me?
Yes.
Oh, okay, perfect. And can you see my screen as well?
Yes.
Perfect. Also the slides? Not exactly.
Yeah.
Okay, let's try sharing again, I guess.
What about now? Nothing?
Yes, now slides come up.
Okay, and you can hear me as well?
Yes, clearly.
Perfect. So
Okay.
after a short technical issue, I apologize, ladies and gentlemen. It's a pleasure and honor to have this meeting and speak a little bit about the high voltage laboratory as well as show it in the virtual tour. So we are situated in the Budapest University of Technology and Economics, and on behalf of my colleagues, I would like to introduce my colleagues first, Levente Rácz, who is an assistant lecturer and will do the second part of the today presentation, Richard Cherko, who is a lecturer and also the vice head of the High Voltage Laboratory in BME. He will show you all around as a virtual tour during this afternoon. And my name is Balint Nimet. I'm an associate professor in the Budapest University and also the head of the High Voltage Laboratory. In the left side, you can see another logo, which is the Dr. Béla Csikós Live Working Training Center. We also operated inside and also outside in the university, a training center, which is related to live line maintenance that I will show you later on as well. So, short introduction, where we are exactly. We are in the center or center-east part of Europe in Hungary, in a small country. And in the middle of the country, you can see the capital, which is Budapest. And in the middle of the capital is the BME, which is the Budapest Technical University, between three bridges. And you can see in the right side the nice river of Danube, that we are in the right side of the Danube and situated in different campuses. About the university itself, it's a little bit young. The Budapest University of Technology and Economics was established in 1782. And the High Voltage Laboratory is a little bit younger, which was established in 1936. As you can see, a couple of data in the left-hand side related to the students' numbers, instructors, building, programs, doctors, code campus. And we have three main areas. One is the education and research, exactly two. And the second one is research and development that we also doing in the university. I will focus on later on the high voltage area also related to these two main areas. About the faculties in the university, we have 8 different faculties, and one of them is electrical engineering and informatics, where our department belongs to. About the history a little bit, our laboratory was established by Károly Cipernowski, who most probably you know or you already heard his name. He is the inventor of the transformer with the closed iron core in 1885. And also he established at that time so-called Department of Electrotechnics in the BME University in 1893. And also he was the main organizer and the main founder of our high voltage laboratory in 1936. You can see in the middle his character. In the left side, this is one of the first photos that we could find, which was in a different building. And in the right side, this is actually our building where we are now, but back in the past when it was founded by Cipernowski. The Cipernowski laboratory was the predecessor of the today's high voltage and also the live working laboratory, whose new building was constructed in 1959 and 1961. After a big jump from these 1960s, we are arriving to the 2012, and during that time, under our leadership, we did a full reconstruction of the laboratory after more than 30, 40 years. And what these full reconstruction mean, we electrically reconstructed, fully painted, new acoustic flooring, new doors, windows, lighting construction, and which is much more important that the 600 kilowatt transformer was sent to renovation. And also we put a completely new building automatization and also completely renewed all the controlling system of the laboratory. The main devices stay the same, similar like before, as you could see in the left photo, and in the right side photo, you can see just after the renovation that Mr. Cherko will introduce you later on. Who we are, you can see a couple of faces from Professor Emeritus Dr. István Berta, who is the father of the lightning protection and also the EMC, also other colleagues' faces that maybe you could see in several other IEEE conferences. In the right side, you see the three main legs. The first leg is the education that we love to do, and as a university, we also have to do. The research and development, which is the second part, that really our dream, what we parallel with the education, we also doing continuously. But nowadays we also have a laboratory leg, However, it was founded back in the past, a laboratory lab, meaning that we are doing testing based on the IEC 17025 as an accredited laboratory too, and not only just doing the research and development, but because of the income as well, we also need to do some testing procedures as well. Education. Education, we have 3 main levels, exactly 4 or 3+1. It depends on how you making the main categorization. By the way, so one is the bachelor curriculum that we have different classes, as you could see a couple. Also, we are working in a master's curriculum as well as in the PhD level. Our target is that none of any students who are coming to our faculty, minimum once during the bachelor curriculum, will come to the high voltage laboratory and stay minimum 2 hours. Going out without the university, however he or she will be in informatics, he should spend minimum 2 hours. During the master curriculum, they need to be minimum 1 day with a complete course or a complete laboratory testing. And during the PhD, of course, they are spending much longer time in the high voltage laboratory. I think this is a very important target that a lot of people and a lot of students are coming every day to the laboratory. We also have project laboratories supporting our younger generation who are also spending days or doing different tests, as well as involving of building up the tests as well. Also, we have facultative subjects like lightning protection, where we have hundreds of students yearly base, and also several other subjects. The 3+1 or the 4th level is what we call adult education that we started a couple of years back in the past. We have 3 main legs. One is the engineering advanced studies, where we also have lightning protection, EMC, or also the explosion safety. Liveline maintenance, which we started in the beginning of 2000, especially in the laboratory, and we have medium and high voltage training center. And also we are focusing on nowadays the work safety training for DSO and also TSOs, not only for the Hungarian base, but also we are doing training for outside of Hungary, like Turkey and others. Research and development leg. We have the following topics that we are working on, and where we have a couple of results that also I would like to give you a short summary. First of all, electromagnetic compatibility and protection against the disturbance. The second one is lighting and building automatization. Also, we have and we are working on the insulating diagnostics and condition management area. We have results in the industrial electrostatics, mainly simulations, but I will show you later on. Lightning protection, which is one of the first and the main topic in the laboratory, started by Professor Dr. Tibor Horváth, who was the father of the lightning protection and who made the first IEC standard in the world. He used to be our former boss and also working in the university. Liveline maintenance, which is one of the latest topic, and the latest one definitely is the improved line operation. These last 2 topics will be discussed more detailed later on. First of all, I would like to go through the first 5 main areas. Lightning protection. As I mentioned, just a couple of information and results from the past and also from the present. The probability modulated attraction space theory, shortly PMES, which was supported and invented by the mentioned Professor Tibor Horváth, as well as the much more well-known rolling sphere method, which is part of the IEC standard, was also established and also done in the high voltage laboratory, including the simulations as well as thousands of measurements on those devices, which we'll introduce you later on. Lightning protection, the newest and the latest studies and also latest area that we are working on, a never-ending story for sure of the lightning protection, especially for the renewables, wind turbines, and also solar panels that we are working on introducing and using those main features which was invented and developed by Professor Horváth and Professor Berta. And also the latest area and the latest topic is the preventive lightning protection, which was especially my field as well, back in the beginning of 2000, which is another area how we can use and how we can make a lightning protection for different areas, not just putting up a lightning rod during the secondary protection, but as well as protecting thousands of people, for example, or protecting a Formula One. Industrial electrostatics, which is another topic. We are involved in several international committees involving IOP, for example, and also in Institute of Electrostatics. In this area, we are mainly working on the simulations, as well as we don't have so many electrostatic precipitators in our area. However, a couple of power plants we also have. And we have three colleagues who are also working internationally based in this field. Insulating diagnostic and condition management, which is the next area. You can see also several SIGRE, IEEE, and other areas where we are continuously involved. We were part of, for example, the first RVM measuring device improvement in the beginning of 1990s, as well as we did a lot of work in the health index area, for example, or also online testing in the transformer, in the SIGRE working groups, and also in the cable diagnostics. We have several results, for example, online measurement and monitoring systems that we developed, as well as cable diagnostics and lifetime management, and also the transformer sensoring, as I mentioned you earlier. Lighting and building automatization, we had a lot of results in this area until the big company GE had a big manufacturer as well as research and development center here in Budapest. Nowadays, we are just following what is going on the market and have some nice agreement with, for example, Phoenix Contact or Schneider Electric, and doing the building automatization part of it. Electromagnetic compatibility and protection against the disturbance, which is mainly concentrating on the different EU regulations, as well as doing simulations and studies for overhead lines, medium, high voltage, and also for the everyday people as well, continuously. We also have some results and also developments related to the overhead line, when we are getting closer to the potential, and when we are speaking about lifeline maintenance. One of our other big area is how we can protect the human, how we can make the adequate protection for the worker, especially during lifeline maintenance, including conductive suite, for example. And finally, we are arriving the live working and the vicinity working. As I mentioned you, the laboratory started this area education as well as research and test and tool testing in the beginning of 2000. However, Hungary was the second in the world who started just after Canada. The high voltage live line maintenance, the father of this area is Dr. Béla Csikos, who is who we follow his name in our education and training center. We are very much involved in SIGRE as well as IEC as well as IEEE in different areas, and also we used to be the first organizer of the ICOLIM conference in 1992, and also later on the 11th one was here in Budapest. Just to jump into our latest development, which is the protection against the induced voltage and current. We developed a new test method in the high voltage laboratory in the last couple of years, which is under involvement by the ASTM standard and the new standard related to the conductive suite, especially the AC induction conductive suite will come out at the end of this year, hopefully, or latest beginning of next year. This protection is a special protection, gives the enough protection for the worker if we are speaking about, for example, a double circuit power line. As you can see in the middle, the left side is switch on and the right side is switch off. And if we are working in the switch on side, in the left side, it means that it has live line maintenance. If we are speaking in the right side, which is switch off, however, we are following the grounding and the EPZ zoning and all other techniques which is used by the different utilities. Unfortunate cases happens, hazards and also failures and accidents happen. So in this case, we can have a special personal protective equipment, the PPE, that the people can use. All this PPE was developed by the university, and also we have a final product which is on the market almost 5 years. Of course, this is not only used during the overhead line work, but it can be also a lot of advantages in the railway area as well. You can see in the left side just a schematic photo about the test method, which was completely developed here in the university. So once the product, but not only just the product was developed, but also the complete test method was done in the lab. And also why we need it, just in the left down photo, you can see a nice arc just done by one of our US colleague, removing the grounding from the conductor, and you can see the arc which is there because of the induced voltage and current. This suit gives enough protection against 50 ampere during half a minute. Last but not least, moving forward to the training center. As I mentioned we have an outside medium voltage training center, which is close by the university. And this training center, we introduced different structures, especially all different structures which is available in the Hungarian network. And we can do the so-called hot stick method in the left side, and also we can do the bucket truck version, meaning the rubber graph technique as well. A couple of European projects, and one European project which is back to the best pass area and the FP7 area, namely the best pass project. In this project, we had a couple of development. This project was focusing on HVDC. However, it has also an AC work package where we were involved as well. And we developed the DLR technique that we started at that time. Very shortly, just about the dynamic line rating, it will be introduced much more detailed by my colleague, Dr. Ratz, in the following minutes. So here in dynamic line rating, we were focusing not only just the algorithm, but also the sensoring technique, how we can build up a dynamic line rating from the zero, from the scratch, how does it look like. And nowadays, almost each of the European utility, we have some cooperation in this field. Improved operation, which is the so-called or part of the dynamic line rating area, where we developed different forecasting system, also real-time measurement, involving also the icing alert, anti-icing, and also not only just focusing on the physical model, but we also have some experience in the AI supported, we call black box model of the system too. The laboratory, as I mentioned, has two main accreditation, or one accreditation, one notification. The accreditation is based on the Hungarian Accreditation Authority, and we have a 17025 certificate of the laboratory. As I mentioned, we have education lab, we have the research and development, and this is the third, like doing just commercial testing based on the IEEE standard and following it. We also have a notified body, a notification, which is a designated body in the railway electricity, which is also during the recent 4 or 5 years, we are doing several jobs, mainly in Hungary, but also in the European level too. Conferences, just a little bit go back in the past, almost 10 years before we organized Electrostatics International Conference, then 2014, the International Conference on Live Line Maintenance. Moving forward, 2018 was the the IEEE conference, which is the second international conference on dielectrics. And just after 1 year, we organized also the well-known International High Voltage Symposium, ISH 2019, also here in Budapest. And references, we have thousands of references coming back from or starting from 1936. However, this is just the last 5 years of different smaller or bigger company names that you can see on the slide that we are working together. As you can see, mostly or mainly we are working to the international level. However, we also are very proud of the Hungarian partners that we have also continuous cooperation. Ladies and gentlemen, thank you very much for your kind attention. If you have any question at the end, you will have the possibility. Now I would like to leave back the floor to Dr. Ratz to continue with his part. Thank you so much. Just give me a sec and then we can continue, ladies and gentlemen. Yes.
Good afternoon. Can you hear me?
Yes, we can hear you, but we cannot see your screen until now. Maybe, just give me a sec. Yeah, now it's good. You can continue.
Okay, thank you very much. My name is Levent Ratz and I work in the high voltage laboratory as Balint mentioned, and in the next few minutes I would like to talk about laboratory tests and R&D activities in the high voltage laboratory. As Balint mentioned, we have so many fields in which we do research and development. In this short presentation I would like to focus on 3 different areas, which are the live working, vicinity work and dynamic line rating. As Balint mentioned, we are an accredited laboratory, and this is important because in case of live working and vicinity work, the key word is the safety, and this means that the tools and the personal protective equipments need to be tested regularly on a yearly basis. And in this laboratory, we can do such tests on medium voltage and also on high voltage level. In medium voltage, you can see here some rods, some insulated rods, which are used in the industrial fields. And we do tests on these rods and also gloves and blankets on a regular basis. If we go from middle voltage, medium voltage to high voltage, the principle is different because in medium voltage, the principle is insulation, but in high voltage, the principle is the Faraday cage and the conductive suits. And you can see an example of conductive suits which are used on high voltage power lines. Our colleagues was the first in the world who recognized that this Faraday's cage can work well only if there is a proper phase mesh. And you can see here some graphs about the effect, what happens if a conductive suit has no phase mesh. We were working also in writing standards, and we did a lot of simulations, and as a result in the field you can find proper conductive clothes which has a phase mesh, and in this way we can ensure the safety of the workers. If we stay also at live working, and there are different tools which are used also in Hungary and all around the world. And one tool is a conductor car, which is a device that can go up to the conductor, and in this way a lineman can do different works like changing insulators or spacers or dampers. Within the project named PES, this was a European Union project, we did development of a special conductor car. The novelty of this device is that it is made of non-conductive parts, and in this way it is super light, and it has a special feature that it can it can go through the insulators, as you can see in the picture in the middle. The total development was made in the high voltage laboratory. We did electrical simulations and also mechanical simulations, and the result was prized at the IEEE conference, which is live working conference in Europe. This is another development which was made also in the framework of the PES European Union funded project. This technology is called insulator replacement, and in this way the lineman can change the suspension insulators of the power line, and you can see here an insulated chair which is also super light, and in this way it can approach the conductive material of the towers. If we move from live working to vicinity work, it's important to note that there could be problems also if you do not do live working, but work next to the high voltage parts which are live, and this situation can happen, as Balint mentioned, in double circuit power lines and also railway systems. And because of the capacity coupling, there could be induction voltage and inductive voltage and also inductive current in these dead parts. And this is important because of the safety aspects. We did some simulation and also some field measurements in Hungary, and you can see here 400 kV power line tower. and we did some modeling and simulations, and you can see that in the different phases, the maximum induced voltage could reach almost 20 kV, which is very, very high. And in this way, we have to make some proper protection against the induced voltage. If there is an induced voltage and the grounding is not proper, there could be induced current, and this can also have problems for the linemans. And here is an innovation which can be also found on the market. For live working, we use conductive suits, and these kind of conductive suits were modified a bit, and these kind of PPE can be used also for vicinity work. The principle is that this conductive suit has very low resistance conductive tapes, and it can shunt the current, and in this way it can protect the worker, and they can work also on dead parts of the double-sided power lines. You can see here that these kind of suits can shunt 50 amperes for 30 seconds. So in this way, there will be no heat and no arc and no problems inside of the clothing. Here you can see some figures which were made in the laboratory, because in the laboratory we were created the acceptance and periodic testing criteria for this clothing. At type test, there is destructive measurement. In this way, we put this clothing into a circuit and we increase the current up to 50 amps, and we leave this current until 30 seconds, and we check whether it destroys the garment or not. You can see that if the garment is not proper, there could be overheating and also arcing, and in this way we can test the suit. If the type test is okay, we have a special model for the resistances, and we can check only the resistance and calculate the induction current from these values, and in this way we don't have to destruct the clothing. The third topic is dynamic line rating, or shorter form DLR. This is my work. This is my research topic, and the aim of this topic is that high voltage lines need to be flexible, and we have to integrate so many renewable energy sources in Europe because of the carbon neutrality. And in this way, there are aging power lines, and we have to handle these flexibility issues. So the core idea is that we put weather stations on the towers and also put line monitoring sensors on the phase conductors. And in this way, we can measure the weather parameters and also the conductor parameters. What DLR can do? If we monitor these parameters in real time, we can calculate the line rating from time to time. And this is useful because in this way we can increase the ampacity of the power lines by 20-30% in 95% of the time. So it is very significant. There are so many benefits of this method, like better utilization of the grid, and we can combine this also with protection against icing and extreme weather conditions, which can be useful in Nordic countries. Here you can see a power line which is equipped with sensors and also some concept about the dynamic line rating. Regarding dynamic line rating, there are so many European Union funded projects that we were involved. You can see 3 of them. First was the BES PES project that Balint mentioned, because this project had a live working part also. And after there was FlexiTranstor project, and the last one is the FARCROSS. This is just ended last month. Some words about what we did in these European Union funded projects. The first was the BES PES project, and in this project we were involved in sensor testing. We did different kind of tests like icing test, ESD test, and vibration test, and we tested a real sensor, and we accredited this device to be used in the field. The FlexiTranstor project was made because in Slovenia in 2014 there was a massive icing and so many towers collapsed and power line conductors damaged. And the core question was whether we can make an ice prediction system from the weather forecast. And you can see here our model. This can detect 3 kinds of icing, and we can say the ice layer and also the extra weight due to the icing. And if we heat up the conductor, if we detect these kind of events and heat up the conductor, we can ensure the safety of the line, and we can we can have safety. You can see here some picture. This is an OTLM sensor on the line, and this is a camera, and you can see here an icing event. And this is good because in this way we can validate our model, and you can see here that our model noticed this icing, and in this way it was validated. This is a laboratory test, which is also important, and this was made in here in the high voltage laboratory. This is a high current facility, and it is important because we have to investigate how the conductor reacts if we increase the current, and you can see here the thermal behavior of the conductor. So in this way we can validate the sensors. And last but not least, some words about the FARCROSS project, which has ended last month. In this project, 4 countries were involved: Austria, Hungary, Greece, and Croatia, and 2 different dynamic line rating systems were structured. One is based on direct conductor temperature measurement. The other one is based on LiDAR measurement, and we compared these sensors and systems, and we also make some improvements. The first was that BME improved a DLL algorithm, which can work without the use of weather station. This is a big innovation on the market. We have an ANN, which is artificial neural network, an ANN-based conductor temperature tracking model. This is useful because if we put sensor on a conductor and we train a neural network to detect the behavior of the heating and the cooling of the conductor, after 1 year we can relocate the sensor. So in this way we can save money. You can see here the accuracy measurements of this model, and as it was in the FlexiTranstor project, we have an icing alert system, and it was also improved with load forecast. So in this way, the false positive results can be removed. And one more thing, we have an improved sag calculation model, and in this way we can make a digital twin for the power line, and we can calculate and detect the sag and clearance behaviors in real time, which can be very useful in Europe. Thank you very much for your attention, and I would like to give the word to Richard, who will make some interesting laboratory tests.
Good afternoon again. I am happy to show you our very first device. Just behind me is our 250 kilowatt transformer that makes 250,000 volt AC voltage. So it is generating 50 hertz AC voltage. This is the very original transformer of our laboratory, and we are actually very proud to still be using it. Despite it's old, we still need the very same high voltage for testing. The question arises why we need testing. We have lots of models, we have finite element calculations, but the fact is that in case of high voltage, it is basically impossible to take everything into account on one hand. On the other hand, it is also important to mention that despite we have models for breakdown, for flashover, for discharges, these usually work for only a specific setting, for specific electrodes, specific gases, specific insulator surface. And actually in the real field, we also have contamination, we have microscopic protrusions, we have moisture. So basically all the time, before we put anything that works with high voltage into operation, we need to do the actual testing. We need to do it at AC, that's the operating type of voltage. So this is a 250 kV transformer, but if I turn around, we have a bigger one, a bigger system that is 550 kilowatt transformer. Actually, our laboratory has a 600 kV transformer, which is under repair right now. We are quite proud of that occurrence, that we did regular diagnostics of the transformer, and we realized that there is something going on in the transformer. Ultimately, it needed a bushing repair replacement. And we found out based on dissolved gas analysis and partial discharge measurement here at our very laboratory. However, it is not only the AC voltage that occurs on the high voltage devices. We also have lightning impulses because all the high voltage stuff operates outside, so we cannot avoid lightning strikes. So for this reason, we have lightning impulse generator. This one has higher energy, but lower voltage. This can go up to 600 kilowatts. The other one, the older one, has a bit of lower energy. However, it can go up to 800 kilowatts. As you may have seen already, we also have a part of a power line in the lab. This is a small portion of a 400 kilowatt power line. And we can do here education of the line workers and testing of the devices that are being developed here. And now I'm turning to our first experiment that I will show you. And for this, I'm asking for 1 second of patience. So I will change my camera to show the experiment a bit better. Yes. I hope it's okay now, and I'm asking now my colleagues for help. So what we are going to do right now is one of the basic experiments and basic knowledge in high voltage. We will put high voltage on that copper sphere on the left, and on the right side we have a grounded metallic mesh, and in between there is a glass insulator. And as the voltage is being increased, we can hear discharges starting. I will show you where the discharges occur. So this was quite loud, I guess. I will wait for my colleagues to ground the arrangement. Obviously, I don't want to get electrocuted, so now it's grounded and I can go inside myself as well. So what's very interesting here, what we have seen, is that the discharges occurred on the surface of the insulator. They came here along very, very long way, despite there was this very thin glass between the high voltage and the grounded part. And the reason for this is that the surface of the insulators is always the weak spot because of contamination, because of moisture. It's always much, much weaker, by orders weaker than the material itself. So this is the reason, if we look up on an insulator, on a power line insulator, that they are so long. Actually, if you look at the material itself, the material could have been much, much smaller. If you look at the insulation of a high voltage cable of the same voltage, that will have only like centimeters of insulation. However, in the outside, if you have a surface, if you have a free surface where pressure work can occur, there you need this very long insulator. Next, as Balint and Levente also told you about, we are also testing live line suits. This means that the workers go on the power lines while it is energized. It is at, for example, 400 kilowatts. However, they are wearing a suit that has a metallic mesh in it, so it works as a Faraday cage. However, Faraday cages are not perfect, so we need to do actual testing, and we need to see whether there will be a body current, a current flowing through the worker's body that is harmful or not. This was the original and the basic testing that the EIC standard required. And so we put together a testing arrangement where we use a metallic plate that is energized. We will put 100 kilowatts on it. The clothing and the mannequin is in the high electric field. And we have cables that allow us measuring the current that is flowing through the suit and the current that is flowing through the mannequin as well. So when we are energizing, you can see in the oscilloscope that the voltage is being increased. And we can measure the current that is flowing through. This is the current that we see right now that is flowing through the suit. So this would have been the current flowing through the worker if he wasn't wearing the conductive suit. However, if we check how much of the current is flowing through the body, it is only a very small portion of it. We are actually not talking about percentages, we are talking about decibels. This very clothing has a suppression ratio of around 40 decibels. Okay, and then I will show you, of course, I'm grounding again for safety. And what we have mentioned is that in the older version of the standard, it didn't require the use of a face mesh. And the problem was that the average protection for calculated for the total surface of the body was good and acceptable. However, if we calculated the electric field that reaches the eyes and the face, it was over the WHO requirements. So let's see what different makes if we use the face mesh right now. Anyway, this face mesh was originally included in the Hungarian design of the live working clothing. And now my colleagues are increasing the voltage to the same level as previously. And the clothing current is increasing to the same level. Okay, but you can see that the body current is now 30-fold smaller. And this means basically that all this current was flowing in through the phase. And well, with our developments now, worker safety is much better. Okay, for the next experiment, I will show you lightning strikes. The main question of lightning protection, of primary lightning protection, is where the lightning actually strikes. If we have a structure and we put on lightning rods, if we have a smaller and a bigger structure, then where the lightning will strike. So let's see that in our small arrangement how this will happen. The capacitors are being charged, and they will be quite quickly, and the results are usually quite spectacular. So the lightning current made a big damage to this tree that was inside. Naturally, this experiment this way is only a little show, so but if we make these experiments like 1,000 times and check where the lightning strikes in case of a wind turbine, for example, then we can test whether the lightning protection that was put in place operates correctly or not correctly. So for example, in case of wind turbines, it's very important that the lightning strike should attach to a metallic point, a lightning attachment point. Because if the blade itself is hit by the lightning, then it will break the blade, and due to the imbalance, the wind turbine will fail totally. You can check this in YouTube. There are very spectacular videos. Okay, so basically, I think our time is up. We are very happy to answer you any questions. And if you happen to come to Budapest, just send us a message, and we are very happy to show you around in live. Jen, I don't know if we have any questions. I don't see the chat right now.
Yes. Thank you very much. To be honest, there are no comments from the platforms, LinkedIn, YouTube. It's very interesting. I see this shocking. And previously, I was at Cardiff University, so I was involved in that best path project for a while. Yeah. And I think the questions for the audience, if you have any questions, you can easily find the email address online on these presentations, and you can drop email to them to ask any questions if you are interested in. And for the interest of time, I think if we have no other things to discuss, if you have more, no, or we can close today's event. And thank you very much for your time and efforts. It's very interesting and very helpful for others. Maybe you can attract more students to join your lab in the future from this advertisement from HP platform.
Thank you very much. They are absolutely welcome.
Yes. Thank you very much. Thank you. Bye-bye. See you next time.
Thank you.
Thank you. Goodbye.
Bye.